In this video, we are going to look at integrating using partial fraction decomposition. In our first example, we see that if we had tried to approach this using u substitution, by choosing u to be what's in the denominator, then our du would be 3x squared minus 1 dx, which does not match the expression that we have in the numerator. So u substitution is not going to work for us. So instead, what we're going to do is we're going to take the integrand and we are going to decompose it into partial fractions. To start that process, we first factor the denominator completely. To factor the denominator completely, I will pull out the GCF of x, which leaves me with x squared minus 1 inside the parentheses. X squared minus 1 can be factored further. It is a difference of squares. It factors into x plus 1, x minus 1. So now we have the denominator completely factored. And with that denominator completely factored, I can see that we have three distinct linear factors. We have a linear factor of x, a linear factor of x plus 1, and a linear factor of x minus 1. So when we begin to decompose this into partial fractions, we will need to find some coefficient a that will go over the linear factor of x, some coefficient b that will go over the linear factor of x plus 1, and then finally some linear factor c. I'm saying linear factor, but I just mean number, some number c that will go over the linear factor of x minus 1. So a, b, and c, these are all real numbers that we need to find. Because if I knew what these real numbers were, then I wouldn't have to integrate that expression that we're not able to integrate. I could integrate all 1, 2, 3 of these individually because these are the exact same thing. It's just that we would have broken it into partial fractions. I will mention that partial fraction decomposition is a topic from 171. So the method that I'm about to go through of finding A, B, and C is something that you have already learned. If you need a little bit more help with going through this, please feel free to let me know, and I'm more than happy to meet with you one-on-one and work through that. So to solve for A, B, and C, I'm first just going to rewrite the equation. And now within this equation, I want to eliminate all of the fractions. I want to get rid of every single denominator. And so to do that, I need to multiply all 4 terms in this equation by the common denominator of x times x plus 1 times x minus 1. So starting on the left-hand side, when we and keep in mind this x times x plus 1 times x minus 1, that's all over 1, right? So when I multiply the left-hand side by that term, the x will cancel, the x plus 1 will cancel, and the x minus 1 will cancel, and simply leave us with the numerator of 3x squared minus 7x minus 2. When we move on to the a term and multiply, only the x will cancel, and a will be left multiplied by x plus 1 multiplied by x minus 1. Moving on to the b term, the x plus 1 will cancel, and b will be left being multiplied by x and x minus 1. And then finally for the c term, the x minus 1 will cancel, and c will be left being multiplied by x times x plus 1. So now we have this equation and we want to solve for A, B, and C. At this point in 171, you would probably FOIL all this out and distribute this, and then you would create a system of linear equations to solve for A, B, and C. I'm not particularly concerned with you solving this using a system of linear equations, so I'd like to show you a more straightforward way to solve this. When we look at the right-hand side of the equation, we have 1, 2, 3 terms. This is an equation. We're solving for A, B, and C. X is a variable that shows up in this equation, but if this is an equation, no matter what the value of x is, both sides of these equations are equal. Both sides of this equation are equal. So we can choose convenient values of x to solve for a, b, and c. And what I mean by convenient values of x is I notice that this term right here has an x factor and that this term right here has an x factor. So if I had chosen to let x equal 0, let's see what the equation will turn into. When x is equal to 0, we have 3 times 0 squared minus 7 times 0 minus 2 is equal to a times 0 plus 1 times 0 minus 1. And when we plug in 0 for x here, this is b times 0 plus c times 0. So these terms completely go away. And now I have an equation that I could solve for a, because this equation tells me that negative 2, since those are 0, is equal to negative a. So I'm taking 0 plus 1 and 0 minus 1, multiplying them, which is negative 1, multiply that by a to get negative a. So we now know that a is equal to 2. Now let's think about what would be another convenient value of x to substitute into this equation. We want to choose values of x that are going to make our factors become 0. At least 2 of the factors become 0. So if I choose x to be equal to negative 1, the terms that have the x plus 1 are going to go to 0. So when x is equal to negative 1, we have 3 times negative 1 squared minus 7 times negative 1 minus 2. Let's substitute in negative 1 on the other side. The a term in yellow is going to completely go to 0, so I'm not going to write anything. The b term in blue will be b times negative 1 multiplied by negative 1 minus 1, and that final c term in green will go to 0. So we will be left with an equation that tells us calculate all of this on the left side of the equation to get 8. And on the right side of the equation, we get 2b, which tells us that b is equal to 4. And then finally, to find c, I'm going to let x equal a positive 1. So that's the equation that we get when I substitute in 1 for x. I'm going to go ahead and simplify both sides of that equation to see that we really have negative 6 is equal to 2c, which implies that c is equal to negative 3. So now that we know what a, b, and c are, we can finish the problem, because that means that this original integral that we started with up here is then the exact same thing as us integrating this with these values for a, b, and c. So for the first term, I'm going to go ahead and break this up into 3 separate integrals, one for each term. A is 2. I can kick that coefficient outside. I'm just integrating dx over x. All these integrals do need to do a dx, so the dx over x is because this x is in the bottom, plus the second integral has b. B is 4, so I'll go ahead and kick the 4 in front of the integral, and then I'm just integrating what's left, which would be dx over x plus 1 from the term in blue right here. And then finally, c is negative 3, so I'll put a minus 3 on the outside of this integral for the last one, where I have dx over x minus 1. And these are all 3 integrals that we know how to integrate. We know that the integral of dx over x is natural log absolute value of x. We also know that the integral of dx over x plus 1 is natural log absolute value of x plus 1. You may need to do a u sub for this one here. For that one right there, if u is x plus 1, du is dx, and you'll see the integral is quickly du over u, which is a rule. We're seeing lots of natural logs show up here. And then finally, similarly for the last term, we have minus 3 natural log, the absolute value of x minus 1. And then we add our constant of integration plus c to get our final answer. So this entire lesson really boils down to, are you able to go through this process of partial fractions to find a, b, and c? And then once you have a, b, and c, you just put them back in, and it's very likely going to land you with integrals that you already know how to integrate using rules from 8.1, basic integration. The variants that we will see throughout this lecture come from what happens when we factor the denominator. So if you can remember in 171 when you learned about partial fraction decomposition, these three linear factors is why we just have A, B, and C in the numerators. We're going to look at different examples where we see different factorizations show up in the denominator, and we'll see how to handle those. So starting example 2, we begin the same way by factoring the denominator. So I'm going to begin by just pulling out the GCF. And then the quadratic that's left on the inside of the parentheses can be factored further because it factors into x plus 1, x plus 1. And so we have x plus 1 squared. So this is not exactly the same case as the previous one because the x plus 1 shows up squared. In other words, you could think it's like this. It's x plus 1 times x plus 1. But I'm not going to write it like that. But I do want to emphasize that it is a repeated factor. So the way we set up the partial fraction decomposition is the first linear factor of x does get a coefficient of a on top of it. Then for the x plus 1 squared, that is still a linear factor, but it's repeated. X plus 1 is linear, but it's repeated because it's squared. So I'll put a b for the factor of x plus 1 that shows up. And because it showed up squared, we put a c over x plus 1 squared. So this is a difference between how we set up the last one. Again, this goes to just the general setup for how you start to decompose within partial fractions. So now I'm just going to go through the same process. I'm going to rewrite the equation and we're going to multiply through and start getting rid of our denominators. So I'm thinking about really just this equation right here, these two sides right here being equal to each other. And I'm coming in and I'm multiplying all four terms again by the common denominator of x times x plus 1 squared. Because I don't want any more fractions within this expression. So on the left side, when we multiply by x times x plus 1 squared, the entire denominator cancels out. And we are left with 5x squared plus 20x plus 6. On the right side, for the a term, when we multiply by x times x plus 1 squared, only the x cancels out. So we have a times x plus 1 squared. In the b term, one of the x plus 1s will cancel out. So b is left multiplied by x and a remaining factor of x plus 1. And then for the c term, the x plus 1 squareds will cancel out, leaving c multiplied by x. And now we're going to make good choices for x values to plug in so that we can simplify this equation. For instance, to get rid of the a and the b term that have the x plus 1 factors, I will let x equal -1. I'm not even going to write the a and b terms because I know they'll go to 0. I'll simplify this equation. I have -9 is equal to -c, which tells me that c is equal to 9. Now, if I want to solve for a, I can let x equal 0 because that will send the b and the c terms to 0 since they both have factors of x. When x is equal to 0 on the left side, those first two terms will just go away and we'll simply have 6. On the right side, we will have a. So we know that 6 is equal to a. Now, finally, I'm going to let x equal a +1 so that I can solve for b. So you will notice that when I let x equal a +1, nothing cancels out and I'm not able to have any terms go to 0. So I do actually have to plug all of this in and substitute and solve, but I still have an equation that now I can solve for c. One thing I will mention is notice here, I didn't write a. I went ahead and put the a was equal to 6. Similarly here, I'm going to erase the c, and I'm going to go ahead and put that c is equal to 9. Then we will be able to solve for b. So I could have chose any value that I wanted right here when I said let x equal 1. I just needed another value to get some numbers in this equation to be able to solve for c. I chose 1 because 1's a pretty convenient number to work with. So let's work on simplifying this equation. On the left side, we have 31. On the right side, we have 24 plus 2b plus 9. Doing some algebra manipulation to solve this, we can conclude that b is equal to -1. So now the problem changes from this original integral that we started with can now be rewritten because we know how to decompose it into partial fractions. I'm going to integrate all 3 of those separately. I'm going to have the integral of a over x, which is 6 over x dx. You can write that 6 on the front of the integral if you wanted to. For the b, we have b over x plus 1. B was -1. And then finally for c, we have 9 over x plus 1 squared. And of course, all these integrals have a dx on the end of them. The first one is a natural log integral. Just talked about that rule. The second one is also a natural log integral. And then for the third one, I'm going to need to do a u substitution. So I'm going to let u equal x plus 1. du is dx. But the point here is that this is definitely something that we do know how to integrate rather simply, considering all the integration tools that we already know. So here I am actually going through the substitution. Notice I did rewrite it because the x plus 1 squared was in the denominator, and so I have the u to the -2. I'll increase my exponent by 1 and divide by my new exponent and add my constant of integration. And then finally, I will just sub back in what u is to see that I really have a -9 over x plus 1 when I integrate that. And we have a plus c. So here is our final answer for number 2. Number 3, we begin in the same way by completely factoring our denominator. It's not completely factored. I can pull out a factor of x from the first factor that shows up in the denominator. That x squared plus 4 cannot be factored. It would be different if it was x squared minus 4, but with the plus sign, we can't factor that. So setting this up, we have a over the linear factor of x plus b over the linear factor of x minus 1. It's not repeated this time, so I don't need a c over x minus 1 squared because this is not repeated. But this factor is not linear. That factor is quadratic. I would like to point out there is a distinction between this factor down here that is quadratic versus this x plus 1 squared here that was a linear factor that was being repeated, right? It was different down here in number 3 because I can't factor x squared plus 4. It's an irreducible quadratic. It's a quadratic that cannot be factored. So when we're working with a quadratic that cannot be factored as one of our factors in partial fraction decomposition, the way we account for that is we put a linear factor on top of that. So what does a linear factor look like? Well, it looks like mx plus b. But keeping in with the letters, we write cx plus d. There, so we have the partial fraction decomposition set up. Again, I want to just emphasize this one looks different because this in the denominator is a quadratic that cannot be factored. Again, that goes back to just how partial fraction decomposition setup work, which is a pre-calculus objective. Now let's go through and clear out our denominators. So I'm multiplying everything in this expression by the common denominator. So take a second and work through that algebra. Think about what cancels and what does not cancel as you multiply through that common denominator. Now I'm going to start choosing some values for x to solve for some of these terms. So I chose x to be equal to 1 because I know that my a term will go away and my c term will go away. So I'll only be left with the b term and I'll be able to solve for b. To conclude that b is equal to -2. Now I will let x equal 0 because then I will be able to solve for my a term. So we have some values so far, but we do not have C and we do not have D. And notice that there are no more values of X that I can plug in that would make the A and the B term go to 0. And we could do what we did last time, where we just chose a random value of X. If you remember the last example, I just chose X to be equal to 1 to help me find the third one, and I actually had to do algebra to solve. But here I have 2 that are missing. So if I just let X equal some random number, I'm still going to have C and D showing up in the equation that we need to solve for. So ultimately what we're going to have to do is we're going to have to solve a system of equations to solve this. I want to show you a particular method. This is probably the same method that you worked with in 171 if this was a topic that you covered, but it's called equating coefficients. So the first thing I'm going to do is I'm just going to rewrite this equation down here, and I'm going to substitute in that I know that b is equal to -2 and that I know that a is equal to 2. Okay, so I've substituted in for b being -2 and for a being 2. And now I just want to simplify this expression out and do some algebra. So I'm not going to work through all of it, but I do want you all to take a second and actually FOIL all of this out in here, distribute this in here, combine, distribute in there. This you would need to multiply together first, probably to get x squared minus x, and then you would FOIL that with the cx plus d. So take a second and work through that algebra and see if you get the same thing that I got. So I have that all multiplied out, and now what I'm going to do is I'm trying to solve for C and D. Remember, I'm trying to solve for C and I'm trying to solve for D. So what I'm going to do now is I'm going to move some things around to start simplifying this equation. So the 2x cubed and the -2x cubed cancel out. So on the right side of the equation, the only term that has an x cubed is the cx cubed, which I'll write in the front. Let's see what terms we have with an x squared. We have a -2x squared, we have a -cx squared, and we have a plus dx squared. So all the terms for the x squareds, I'm going to pull the x squared out, had coefficients of -2 minus c plus d. So what I did is I took the terms that I underlined in red that all have an x squared in common, and I factored an x squared out of them. Now I'm going to do the same thing for all the terms that have an x. There's a -dx right here, and that's the only term because the -8x and the +8x cancel out. So we have a -d in front of an x. I am going to write this a little differently. I am going to put a plus sign here. And I'm going to wrap the -d in parentheses, and then I'll put the x here because I'm really trying to emphasize the coefficients. And then finally, there's a -8 that's left over. So now that we have this written in this very particular way, let's look at both sides of the equation. On the left side of the equation, we have a 2 in front of x cubed, and on the right side of the equation, we have a c in front of x cubed. But if these two things are equal, then the number in front of x cubed on the left side of the equation has to equal the number in front of x cubed on the right side of the equation. Similarly, on the left side of the equation in front of x, there's a -4. And on the left side of the equation in front of x, there's a -d. But if these two sides are equal, then -4 must be equal to -d, which implies that d is equal to 4. This is called equating coefficients. We are finding the coefficients of x on both sides, and we're setting them equal to each other. Or the coefficients of x cubed, for instance. That's how we figured out that c was equal to 2, because I looked at the x cubed on the right and I looked at the x cubed on the left and I set them equal. It just so happened that this worked out very nicely and I didn't have a lot of algebra to do to solve this. So now that we know all 4 of our variables, a, b, c, and d, we can now go back to the problem and start setting up 3 integrals to integrate that. The first integral will just be a over x. A is 2, so we have 2 over x dx. The third integral is b over x minus 1, and b is -2. So we're integrating negative 2 over x minus 1 dx. And then finally, in the third integral, we have cx plus d in the numerator. So that's 2x plus 4 over x squared plus 4 dx. So now let's actually start integrating. The first two are rather straightforward. They're natural log integrals. The last one, however, is not a natural log integral. If I had tried to do u sub, I would see that it wouldn't work because my du would be 2x dx, but I have a 2x plus 4. And even if I split the integral up, then I could maybe make some progress because I do see this 2x dx and there's a 2x right there. So instead of writing this integral as 2x plus 4 all over x squared plus 4, I could write this as 2x over x squared plus 4 dx plus 4 over x squared plus 4 dx. So I had to separate that last integral into two separate integrals to complete it. This first one, we will be able to integrate using u sub. That's already what's going on in the corner up here. I can see that this integral just breaks down to du over u, which means that'll integrate into natural log absolute value of x squared plus 4. I went ahead and subbed back in what u is. Then I'll go ahead and bring down what was left from above. For the last integral, that is an inverse trig rule that goes back to 5.8. That is an integration rule for arctangent. So looking back at 5.8, that is this rule right here, because we are integrating 2 squared plus x squared, which does show up in the denominator. So this integral here is an arctan rule. The arctan rule states that the integral of du over, the order in the denominator does not matter, I'll just write it as u squared plus a squared, is 1 over a arctan u over a plus c. In our case, our a is 2 and our u is x. So now I'm just going to be substituting them into the rule, which by the way does mean that our du is dx, so I don't have to do any extra substitution. So we already had a 4 in that integral. I have 1 over a is 2, so I have 1/2 arctan u over a, u is x, a is 2, plus c. So the last thing I will do is I will just simplify that 4 times 1/2 and turn that into a 2. And that gives us our final answer. In our last example, we start off the same way as we did before. We want our denominator completely factored. They give us this denominator already completely factored. Notice the x squared plus 2 on the inside does not factor more. It is an irreducible quadratic, but this time it is repeated because it shows up squared. So because it is a quadratic that cannot be reduced, we do write a linear factor on top of it that looks like ax plus b. And because it is repeated, I repeat it because it showed up squared with another linear factor on top of it. And it's our job to solve for a, b, c, and d. I begin by clearing out my denominator. So now that we have the denominator cleared out, notice that there are no values of x anywhere that I can plug in that will help me solve for any of my terms. And so I'm going to go ahead and distribute on the left-hand side of this equation so that I can start equating coefficients. So I've expanded out the right-hand side. I'm now just going to group my terms so I can actually see the coefficients for each variable. There's only one x cubed term. There's only one x squared term. But as for the x's, there's a 2a in front of an x, and there's a c in front of an x, so I'm going to pull that out. And then for the terms with no x, there's a 2b and there's a d. So now I'm ready to start equating coefficients because I can see what's in front of x on both sides of the equation. So I know that 2a plus c is equal to 13. I can see what's in front of x cubed on both sides of the equation, so I know that a is equal to 8. I can see what's in front of x squared on both sides of the equation because there is no x squared on the left side. So that means that b must be equal to 0 because there's like a 0x squared here. And then the term that has no x, the 2b plus d, must be equal to 0 because there is no term with no x on the other side. There's like a plus 0 there. So now that I have all of these equations, first let's just use what we know. Clearly we can conclude, we know b is 0, so we don't have to worry about that. We can also see that d is equal to 0 because if b is 0, d is 0. So both b and d are 0. A is 8, so I know that this is 2 times 8 plus c is equal to 13. So we can solve and see that c is equal to -3. So now we know that the integral we're trying to integrate is really just ax, which is 8x over x squared plus 2. There's no plus b because b is 0, so we can end that integral with a dx. C is -3, so we have a -3x. There's no plus d because d is 0. And I will end that integral with a dx. So now we have these two things that we need to integrate here. The first integral I can do with a simple u sub because the denominator has degree 2 and the numerator has degree 1. So when I pick up this 2x dx for du, I can choose to multiply both sides by 4 to see that 4 du is 8x dx. So when I do the substitution, I'm actually integrating 4 du over u, which means I would have 4 natural log absolute value of u after I integrate it, which would be 4 absolute value of x squared plus 2. Absolute value isn't actually necessary there. X squared plus 2 is never greater than 0, so it's fine to write that with just parentheses. Plus, let's go work on that second integral, which is a little bit different because the denominator has this squared factor that shows up in there. But let's see if a u sub will still work. If I let u equal x squared plus 2, du is 2x dx. I don't have a 2x dx, but I can manipulate this equation and see that 1/2 du is x dx. So -3/2 du is -3x dx. So when we actually do the substitution, we have -3/2, the integral of u to the -2, because remember it showed up squared in the denominator, du, which integrates to -3/2 u to the -1 divided by -1 plus c. So those minus signs cancel out, and that u to the -1 sends the u to the denominator. So we have 3/2 with u in the denominator. Remember that u was x squared plus 2. And then I will remember to add my constant of integration plus c. And then we have this expression integrated.